In this one, we will take care of this shape between these two graphs, which namely are 4x plus 5. That's the linear one, and this. So basically, 4x plus 5 is this line that intersects y at 5, and then we have x squared that goes beneath it. And there's some interval on which x squared is smaller than 4x plus 5, namely until this point. So we were taking care of some interval from 0 to the point till when x squared is below 4x plus 5. And that point we can somehow find in a second. But the point here is that, yes, we have some bounded area, and I want to find the centroid of it, which is something like the average location in this area. And I want to get the exact xy coordinates for it. So something like the center of gravity for this shape. So first of all, I could calculate the area itself, how big that area is. For that, I will need some integration. But the point is that I first also need to know till when. So yes, I'm considering that I begin at, but actually let's say we make it even more natural. And what I will do is I will take really the area since the first point where 4x plus 5 is beyond x squared till it still applies, and then when x squared is above again, then we will stop. So actually, let's say we do not start at 0, but we'll start already at some point here left of the y-axis. So this whole area. So it's bounded by 4x plus 5 and below by x squared. And so all the area where 4x plus 5 is higher than x squared, on that interval, the area bounded by 4x plus 5 and x squared from below. So all this area, and I want to find the centroid. So perhaps from an approximation perspective, the centroid could be more to the left now. And okay, so I want to take this whole area, want to find the centroid, want to find the xy coordinates. But first of all, let's take the area of it. The area of it will be the integral of the difference of the two functions, of the bigger one minus the smaller one. So 4x plus 5 is the bigger one on the interval that we're looking at, minus x squared, which will be the smaller one on this interval. But we also need to know where are the boundary points for the integration. If I was integrating beyond them, to the left of this one and to the right of this one, I will be changing the value. I really need this area, so I need to integrate from x1 until this x2, where this applies. And to find these values, we can look at 4x plus 5 equals x squared, the points where the y's of the two functions equal. And this can be solved like a quadratic equation. And these 2 points namely end up being whole integers, which is useful. They're 5 and minus 1. So we identify that this is minus 1 and this is the 5. So we know that from minus 1 to 5, 4x plus 5 is bigger than x squared. And that is the subject of our integration now. And still, our main point will be to find the centroid afterwards. So now we're just doing the area, but we know that it's going to be from minus 1 to 5. Alright, so integrating this, we have to evaluate things. And things will simplify. And furthermore, the result will of course be a constant. So this, and then we have this, and this is also fine. So we might want to make the denominators the same. And actually they're both 1/3, all of them. So it's 108 over 3. So that's interesting. So we have that. And partially is minus 9 plus 1, so minus 8. This one we make it positive. Okay. So the area, this area is 108 over 3. And actually this figure will be needed because we'll be using it onwards. And so let's continue. So as I said, to find the centroid at some point, in this case it will be actually inside the area. And sometimes for some shapes it might actually lie even outside the area that we're considering, but in this case it will be inside it somewhere. And we need the xy coordinates. We need to define this point concretely. So what are the xy coordinates? So this is centroid C, defined by xy, usually with bars above them. And now I need to define x and y. So for a centroid, the x is defined as 1 over a, which a is the area, we calculated that before, of the shape, times integral of x times the difference of the two functions. So the two functions are the big one minus the smaller one. Well, so the bigger function is 4x plus 5, smaller one is minus x squared. So difference is this, and the difference multiplied by the x, and an integral of that over the region that we're considering, which is where does this area take place? Minus 1 to 5. And y bar, I will show in a second how to get that coordinate, and it will be actually a different one. So similar but different. So for x bar, we use this formula, and a we have. So 1 over a is 3 over 108, and then this integral. So that's going to take a second to carry out, although fortunately it's polynomial. First we might actually simplify and collect some terms. So we can integrate straight away actually. And minus 1. So 3 over 108, and this is mechanical work basically. We have 500 over 3 minus this minus this. So different denominators making it a little less practical, but still we can make it. And then we also have to subtract the lower bound evaluation. So there's that. And then all in all, the result will end up being something where we will have to play with a lot of fractions. So that's actually gonna take a while because there's a lot of fractions. So over 3. So this is 375 plus 4, 379, minus 1, 378 over 3. So 375, and then we have plus 4, 379, minus 1, 378 over 3. Actually, we have to also take care of the halves, and halves will be minus 125 plus 5 minus 120 over 5. And now we can further work with this number, but I'll leave it to later because that would take so much time. So actually we got the x coordinate. So the x coordinate is 3 over 108 times this. And let's now also cover the y coordinate. which will be similar. But a different formula. So for the y coordinate, it's 1 over 2a times, not x times the difference of the functions, but it's the bigger function squared minus the smaller function squared. So here namely it will be 4x plus 5, again from minus 1 to 5, minus x squared dx. So there will be some big powers, that 1 over 2a is actually a little different, it's going to be 206 over 3, and multiplying by the integral. And this is going to be 16x squared plus 40x plus 25 minus x cubed dx. And again, this you will have to evaluate and so on, which let's say I will not finish this because it will take a lot of unnecessary time. But in general, you get the point here. So I will sum up our results and we'll wrap it up there. Basically, 1 over 2a once again is going to be 1 over 3 over 100, so 206 over 3, and x bar will be this number. Okay, so with this one we almost made it, 3 over 108 times another fraction, which actually it can be shortened to 126 minus 24. So I mean, we can do some of it. So it's 360 and then, so 126 minus 24. But still, we have 102. So it's 306 over 108. And that's only 153 over 54. And that's going to be 51 over 18, and there's going to be 17 over 6. Alright, so the x we got actually to the number that we need. But with this one again, it will take some time, and I leave it up to you. I mean, this is not the point to do integration, it's more the point to understand, or at least remember the method to take centroid, especially between two curves. That's defined by the area between some curves. So to revise it all, what we did is we considered some area between two curves. We also have to know, okay, if we're considering the area where 4x plus 5 is beyond x squared, we need to know the points that bound that. And the points that bound that are the solutions to the solution to the equation where these two are equal, x squared is equal to 4x plus 5. Get the solution via some quadratic equation formulas. And then we know that this applies from x equals minus 5 to x equals 5. And then we apply the formulas for getting the x coordinate and the y coordinate. To get the x coordinate, we do 1 over a, so 1 over the area, times the integral over this region, so from this to this point, of x times the difference of the functions, where the difference is the bigger one minus the smaller one. And for the y coordinate, it is 1 over 2 of the areas times the integral again over the same bounds, but the bigger function squared minus the smaller function squared.